Okay, so this is a video on, it's basically an introduction to electrode potentials. I already have a video on electrode potentials, but I just wasn't that happy with it. I made it probably a year, I guess, more so ago. I don't know how long ago it was. I wasn't happy with it. Re-recorded it only 25 minutes ago. Finished recording, still wasn't happy with it. Went through, processed it, got to about 93%, cancelled it and decided I'd remake it. So this is now the third time that I've done this video. I hope I'm happy with it this time. If I'm not, then I just don't know what I'm going to do, to be honest. I'll just give in. Right to AQA, take it off the specification. So, I'm going to start as I did in the one that I actually have put up, and also in the one that I ended up just sacking off, and that's with a beaker. Now in this beaker, if we imagine that inside this beaker we have a strip of magnesium, and we have a solution containing magnesium ions. So I should put some staple symbols in, really. Let's not be sloppy. So that's a solid piece of magnesium and an aqueous solution that contains magnesium 2+ ions. Obviously something else as well, but I don't really care what it is. Now within this situation here, we would have an equilibrium occurring. And to write it as a reduction, because they like this in exams. Oh, a little hand appeared. They like to write these as reductions in exams. So it would be Mg2 plus 2 electrons, and that's aqueous. I don't like this particular. Yeah, that'd be solid down there. So there we go, the equilibrium that is occurring within here. Now, magnesium's a reactive metal. You should know that at this point. Most year 9s can get to that point where they know magnesium is reactive. You can see it in displacement reactions and all the rest. It reacts with water, albeit quite slowly, but it reacts with acid reasonably vigorously. It's a reasonably reactive metal. So we know that when magnesium, as with all metals, when they react, they lose electrons. They undergo oxidation. So the magnesium goes from magnesium atoms, if you like, to magnesium ions, losing 2 electrons in the process. And that happens very, very easily. It's very happy to carry out that particular process. The magnesium atoms are very happy to lose electrons to become magnesium ions. So if we think about this particular equilibrium that we've got here, this equilibrium, its position will lie really far over to the left because it's really happy undergoing this oxidation reaction. The reduction will happen, but it wasn't going to happen very much. It's going to be much more dominated by this much bigger, or much more likely reaction. As I say, it will lie very much over to the left hand side. We'll have much more Mg2+ and all the rest of it when it finally does reach equilibrium. We can give this a value, and we can give this particular situation here, we could call this a half cell, really, and that only kind of works when it's connected to another half cell, which I'll talk about in a moment. But what I can do is I can say, actually, this is a particular half cell here, and this has a value given to it of 2.37 volts. Now that's quite an arbitrary number at this time. It's classed as its electrode potential, which is where this whole sort of lecture or video, whatever you want to call it, comes from. And what this tells me, having a very negative number there, this tells me that it's very keen to undergo oxidation. It's very keen for this backward reaction to happen, the magnesium to become magnesium 2+ ions. Very, very happy to do so. It's great. Now, if we look at a separate beaker, and let's in this beaker look at a different scenario. Let's look at a piece of copper, metal again, solid, and let's immerse it into a solution that contains copper 2+ ions. There we go. Same principle. We're going to have an equilibrium will form. We've got an aqueous solution there. We've got electrons. And we've got a piece of copper metal. Now this one has a value of plus 0.77 volts. Now what we know here, and you should hopefully know, that copper is much less reactive. We can make pipes out of copper. We can make pans, cups, all sorts of things out of copper. We can do so, particularly in relation to food and drink and water and all the rest of it. We can do that because we know that copper is very, very unlikely to react. It's very, very unreactive. You know, the only sort of the next unreactive ones below it are things like gold, silver, platinum, and all the rest of it. So very, very unreactive. And we can see in comparison these two electrode potentials, that tells us that as well. It's got a positive value here, which I said the more negative noted, the more likelihood of oxidation happening. Well, this is less likely to be oxidized. Now that to an extent depends on the situation that it's in, which I'll come on to probably in the next video. But still, this one has a much more positive value, therefore it's less likely to go and undergo oxidation. Therefore, whereas the magnesium's equilibrium was very far over to the left, this one is going to be more over to the right in comparison to the magnesium's equilibrium. The other way I like to think about this in terms of this negative value versus this positive value here is, and these are arbitrary values, which I'll come on to where they come from in just a second. The way I like to think of this is that magnesium is very keen to undergo oxidation. It's very keen for magnesium atoms to become magnesium ions, in the process of which they lose electrons. Now those electrons are ultimately going to be building up on this piece of magnesium metal here. Boom, boom. All these lines are supposed to be negative electrons. It's just easier than writing E every time. Loads and loads and loads and loads and loads. We get this nice negative value, which is kind of almost giving us an idea of how much negativity, if you like, is within this particular electrode here. On this side, same process will happen, but it's much less likely, particularly in this position of equilibrium, it's more likely that we will get the ions becoming atoms. And so we find this is less negatively charged, if you like, and that actually equates the value, which is positive 0.77 versus the minus 2.37. So very different values. Now I'm not... What am I going to do there? Yeah, let's go on to where these values come from. So these particular values, I said they were arbitrary. They come from something called the standard hydrogen electrode. Now the standard hydrogen electrode, as the name suggests, is a standard. And it's used as a comparison tool. So it has a very particular way that it's laid out, a very particular way that it looks. And you do need to know about it in an exam. You need to be able to draw it, you need to be able to talk about the conditions that it occurs at. And it looks something like this. We have a beaker. I'm going to draw it, we'll draw it about here. We have a beaker, and that beaker contains a solution of hydrogen ions. So an acidic solution, essentially. And what we have in there is we have a lump of platinum. What we do is we pump into this in a ridiculously shaped fashion. We pump into this some hydrogen gas. So we've got hydrogen gas bubbling in, blah, 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 and we've got a solution containing hydrogen ions around here, which is fantastic. And if we would look at this particular, the equilibrium that would be present here, we would find that we have, what are we going to have? 2H plus 2 electrons going to H2, with this being a gas and this being aqueous, just like that. Now, if we take the magnesium situation here, what we can do is we can take this particular half cell and we can connect it to, using a voltmeter, and I'll come on to that in a second, connect it to another half cell here. So there's my lump of magnesium in my solution containing magnesium ions. So what we've now got is we've got this hydrogen here. This is the standard hydrogen electrode. That is this part here. It's not the whole thing. It's just this particular standard hydrogen electrode, this half cell here that involves hydrogen gas and hydrogen ions in solution. We connect it with a voltmeter to another half cell, and what we can do now is we can measure the electrode potential of this particular half cell or any other that we connect here to the standard hydrogen electrode. Now we need to complete this circuit, and we do so by adding, quite cleverly, something called a salt bridge. Now a salt bridge is a piece of paper, tube, whatever it is, needs to be soaked with some sort of ionic solution. Potassium nitrate is a good example. They could ask that in an exam. Which solution would you use? Potassium nitrate is your answer. It allows for ions to move between these two beakers, and thus it completes the circuit, which is what we need. Because ultimately, if a current was flowing, and a current will not be flowing, and I'll come to that in a second, we would find that it flows, electrons would flow around here, and then we need some way of balancing, if you like, between those two in another sense. Now, the reason the current will not flow is because a voltmeter that we use there will have an insanely, almost infinitely high resistance, and the purpose of that is that it gives us almost the highest voltage values you can, the highest potential between these two things here, and that will record something called the EMF of this entire cell, the EMF, the electromotive force. Now, because scientists are nice and they like nice numbers, scientists give this, and this is why I said earlier on these numbers are arbitrary. They're all based around standards. They're only those numbers because they're compared to this particular hydrogen one. It's, what is the value of magnesium compared to hydrogen? Well, scientists are nice, and what they say is that actually, whereas this is minus 2.37 because we worked that out, we do so because we say that this half, the electrode potential of the standard hydrogen electrode, is 0. Which is great. It makes it very easy for us to handle. It's just a 0 value. There's nothing else to worry about there. And now, through some jiggery pokery, we can mathematically, and you are expected to be able to do this as well, you can work out the EMF knowing the electrode potentials. And that EMF is worked out by doing the right-hand electrode potential. And that isn't necessarily from a pictorial format. It's the conventional representation is the best way to do this, which I will show you in a minute. So it's the right-hand minus the left-hand side's electrode potentials. The other way of doing this, and this is something that I'll do more in the next video, I will mention this later on, is that you could say, well, actually this right-hand side here will be the reaction that shows reduction, and this will be the reaction that shows oxidation. So it's the reduction side minus the oxidation side. Now that doesn't necessarily work for the case of the standard hydrogen electrode. It's a very particular example where this rule kind of this works, but it doesn't quite fit into our normal electrochemical cell format because it's being used as a standard to try and particularly work this out. Now, given that we use this as a 0 value, we know this side is therefore going to be 0. So we can just say minus 0.0. So whatever our value is on here, it's essentially going to be the electrode potential of the right-hand side. So for this particular situation, we can say that the EMF is equal to the electrode potential of the right-hand side, which in this case is there, and in this particular case is minus 2.37 volts. Now, normally you would find this value will be positive. Okay, that's a check. But again, this is a very particular example which is geared towards finding a particular electrode potential because of the fact that this is always given this arbitrary 0 value. And that's what it's used. So it's just a comparative, and Chem Guide page, which I'm basing a lot of this video on sort of stuff that I've read in the past on the Chem Guide page. He gives a really nice thing about the comparative point here, and like having long grass and a stick in the grass and things. Some really, really nice page. Look on there, it will give you loads of extra information, but it's comparative. So we can use, though, this concept. This stands true for all electrochemical cells, which is an example, 2 half cells. It stands true in this same format. This way it works a little bit differently, though, in that the EMF is equal to the right-hand side, which is the one we are putting in. And if we'd stuck the copper one in here, we would find that it would come out at 0.77. Now, what we can do is if we go back up to this one here. Now, let's change this slightly. The wizardry of Photoshop means I can just look at this. What I can say is I will do just what I've done there in the standard hydrogen electrode one, and I'll put in a wire, a voltmeter, and a salt bridge. Again, potassium nitrate there, piece of paper, tube, whatever it is. Now I know my value here is minus 2.37 volts, and here my value is plus 0.77 volts. Well, I can use my same principle here of right-hand side minus left-hand side, or my reaction where reduction is going to be shown and my oxidation is going to be shown to give me my overall EMF for this cell. Now, in relation to this is the more negative value. Now, as I said before, the more negative value is the one where you are likely to find, or where you will find oxidation taking place. So this side here, now that these are plugged in together, we would find, and it'd be more so actually if we allowed current to flow, which we haven't done here, we would find that the magnesium is happier to be oxidized and become magnesium 2 plus ions, whereas on this side we would find that the 2 plus ion, the copper 2 plus ion, is more likely to be reduced to the copper ion there. So this is the side where reduction would take place because it's more positive, and this side we would find oxidation taking place because it's more negative. And so to work out our EMF here, we would just do our 0.77 minus 2.37, and that gives us a value of 3.14. Now, there is an easier way to draw all this. This is a very, very messy way of drawing things, really, having all this long sort of all this garbage really over here and all this drawings and all the rest of it. There's a very nice, easy way of drawing things, and that's a method called conventional representation, which takes away from beakers and all the rest of it and simplifies the whole process. Now, conventional representation works by essentially, well, it just simplifies it. So you still include some of the key features. So you include the salt bridge in the middle, and it's just a linear format to show you how an electrochemical cell is laid out, essentially. Now, the way it would work is you put your more negative electrode potential equilibria on the left-hand side and your more positive on the right-hand side. So your oxidation on the left and your reduction on the right. So in this particular format, my magnesium, from the values that I've got here, and I'll just flick back, minus 2.37, that's going to go on my left-hand side. Right-hand side will be the copper. Now, the way it works, you always put your most oxidized species on the inside next to the salt bridge. Anytime you change phase, which is similar to state, you put a line in, which is called a phase boundary, and you just work your way out like this. So that right there, the Mg solid dash blah blah blah, is exactly the same as what is shown here, but it's a much more simple, much easier way to lay this out. And that actually, the way this particularly works is, this is your best way of using the EMF thing here. It's the left hand side there minus the right hand side, and essentially it's the right hand side minus left hand side, exactly as it's written there, which is your reduction minus your oxidation electrode potential. Now, annoyingly, because there's always got to be exceptions, otherwise it wouldn't be chemistry really, what you find is that for the standard hydrogen electrode, it has to be written in a particular way, and that has to be that you still have your salt bridge, but the hydrogen portion always goes on the left, and that ties into the minus that 0 there that I said earlier on. Same bit those before. You put your more oxidized species on the inside, phase boundary up, because we've got differences there, we've got a difference in phase there, gas. What you have to also include here, and this is true of anything that has a platinum electrode, i.e. where you've got gases and solutions, or maybe two different ions in solution, is you've got to include the platinum there as well, and that will ultimately, well, it just shows you're using a platinum electrode there. So this is another conventional representation now, this time showing this particular setup here with the standard hydrogen electrode. What I nearly forgot to include there, and I'm glad I haven't done, is the conditions, actually, just going back to here. The conditions that are required in the standard hydrogen electrode are absolutely crucial. And that's true of no matter what we use on the other side as well. There are a few things you have to pay very careful attention to, and that's that the temperature of this is 298 Kelvin, because it's standard. These are standard lab conditions, or standard temperature and pressures. So temperature is 298, pressure 100 kilopascals, and the concentrations of solutions must be 1 mole per decimeter cubed, and that goes for both solutions used, or all solutions must be at 1 mole per decimeter cubed. That is crucial. This is 3 easy marks in an exam: 298 Kelvin, 100 kilopascals of pressure, and 1 mole per decimeter cubed of solutions. The problem is that if, say, on a different day I do this at a higher temperature, what I'll find is that will affect the equilibrium that's involved, and that will ultimately mean that I will get different values, and therefore they're no longer really comparable. So if I make sure that I'm always using 298 Kelvin, 100 kilopascals and 1 mole, all of these values, the minus 2.37s, the plus 0.77s, all of those values are directly comparable, because they're all being compared to this hydrogen electrode at these particular conditions, which is perfect, which is exactly what we want. We're going to look at one final example, just again it's a bit more of practice really. And that's an example of just another electrochemical cell really, which I'll draw out first off. So beaker 1, beaker 2, beaker 1, it's going to be similar before, it's going to be magnesium, and magnesium 2 plus, this is a solid. This one is going to be a bit of a weird one, and I'm going to put Fe2 plus and Fe3 plus in as solutions, which means I must use an electrode there of platinum. Why is platinum used? It's unreactive and it is obviously a metal, so it is going to conduct electricity, which is important. Seen that question asked before in the past, just be aware of it. We're going to stick a voltmeter in. Beep. We're going to put our salt bridge in. Remember, potassium nitrate, nice and easy, allows for ions to flow. And bish bash bosh stuff. We know we're going to get ultimately we're going to get an EMF value here. Now we've already know the electrode potential for this. You'll be given these values in an exam. That's minus 0. That's minus 2.37. This one is plus 0.77. What I'm just thinking. Did I give that? This value actually isn't 0.77 at all. It's 0.34. I think. Terrible. I'm losing my mind now. I don't even know if that's the right value or not. I apologise. The same thing's true. The same thing is correct. The whole principle behind it, but I've just put the wrong value down. Anyway, this one 0.77 volts. This one minus 2.37. So again, we can see that this one, we've got a situation where we are. This is more negative, therefore this is where oxidation is going to take place. This is more positive. This is where our reduction is going to take place. In terms of EMF, it's going to be our more positive value, our reduction minus our oxidation, or our right hand side minus the left hand side, so it's going to be 0.77, which is going to be exactly the same as what I did in the last one, because I made an error in my numbers, and that's going to be 3.14 volts. Easy. Conventional representation, we stick a nice salt bridge down. We have our more oxidized species going there. This is going to be our reduction side, our more positive. This is going to be our more negative, our oxidation side. So we're going to put our Mg2 plus line there for our magnesium. Now here, because we've got the same phase, we put a comma. We do not put a phase boundary. We do then put a phase boundary for our platinum, but there is not a phase boundary required between the Fe3 plus and 2 plus. And that's really about that. That's electrode potentials in a nutshell. I'm getting a really tickly throat. That's electrode potentials in a nutshell. Any problems, do let me know. I'm a bit happy with this video, I think. Any problems, let me know. There will be another one on electrochemical series coming along, so do give that a look. And that will run through a bit more of this idea, and also a bit more detail about the oxidation reduction part, also linking into oxidizing agents, reducing agents, the feasibility of reactions, etc. So there you go, electrode potentials.